And the process could be based on the similarity of the sequences. And the most simple way to estimate is to find the similarity between the sequences using the distance method. And there are several different kinds of distance methods are using nowadays, but I think the most widely used are the neighbor joining method. We'll talk about it later. And the most simple one is the UPGMA. And it's the most simple, and you can calculate by hand. It's you don't need computer to do the UPGMA. So we'll give you an example for that and to give you an idea how they use. And minimum evolution is the approximate way for estimating the best tree, very similar to maximum parsimony and maximum likelihood on the tree searching process. So basically they are searching for, there are several different trees, like 100 trees there, and how do you know which one is the best? So they calculate the sum of the distance on each of the trees and to compare the whole group of trees and then decide which one is the best. And that's the code, that's called the minimum evolution. But as I am going to demonstrate later, and it's almost impossible to evaluate all the trees. And in other words, we have to find some other ways to approximate the best tree of the data, and without exploring the trees. So let's go through the process itself. In distance method, sequence are grouped based on the similarity. So that's a very simple way. And how do we measure? The simplest way is to measure the differences, like how many substitutions in this example. And there are 4 sequences here on the last example. And the Hamming distance is the number of the differences divided by the whole number of the sequences, which means the total character number. And in this case, for example, the SPC and SPD, and there's one, where is it? One differences between them. So it will be 1 divided by 12 will be 8.3%. So that's the simplest way. And for A and D, there's 16%. So you will know the differences. So it means that C and D are most closely related, probably, than to A. So this is the basic concept. But nowadays we have to incorporate the substitution models, and I think Zhao already talked about that a lot. So I wouldn't go into too much detail, but I would like to reinforce your memory a little, and to use different models on the calculation. And we can use the JER-MING or Kimura or HKY85 or GTR, and these are all very common models for calculating the differences. So the probability for nuclear substitution can be calculated basically on the differences and of there. But basically, if we started with the JER-MING model, and the model here states that the probability of the differences will be equal to this point, and the P will be the direct measure for the observation on the substitution. So in other words, you can calculate K on each pair of the sequences. So for example, for the Y and Z, you can calculate the K is equal to 6 alpha T. So this is something already mentioned about, so I don't need to really go into that detail. And this just give you an example for how we calculate it. And if there's 80 transitions and 20 transversions between the 2 sequences, and the total length is 1,000 base pair or 1 kb, and the number of substitution per site K can be calculated under the JER-MING model. K equals to 0.10732, and the P equals to 0.1 in this case. And under the Kimura 2 parameter model, the calculation, you can just add it up and the P equals to 0.8% and Q equals to 0.02, and the K is equal to 0.10943. And the 2K under two different models are actually very similar. If you only have some minor differences on the third digit there. So basically, the more complex model will give you a better estimate in theory, but it's not always the case. But this is the thing going to incorporate into the phylogenetic analysis, like the neighbor joining methods. So let's go back to the beginning of how we construct the phylogeny using distance method. And the distance method, the major differences between the distance method and the discrete method is they need to convert the original data set into a distance matrix. And the distance matrix is something like the thing on the right. So this is the original data set, the sequence alignment. And this is the distance matrix for 1, 2, and 3, 1, 2, 3, and 4. For 1 and 4 right here, you will see, okay, there are 5 differences out of 7. We put a number 5 here. And there's 1 and 2, that's, there are 3 differences there. So the distance, we put a number 3. So every calculation afterwards only deal with the distance matrix. So they are not going to look at the original data anymore. So that's the major thing and major weakness, I would say, for the distance method, is they ignore all the information on the alignment anymore, but using these distance matrices. But the advantage for this method is very quick. So you don't need to worry about the substitution anymore. You only calculate once, and everything is based on the distance. And that's just numbers, and very easy to calculate. So there's some pros and cons for distance methods. And we'll use this new data matrix to reconstruct the tree. And for UBGMA, the most simple way is to calculate the differences once they can combine the two together and then calculate for the next step. And for example, right here, we'll have a data matrix, the distance matrix for ABCD. Right here, you'll have 6 numbers right here. And if the A and B, it is in this cell, it has the lowest number, which means that they are the most closely related case. So you can just combine the A and B together because they are the most similar sequences. And combine A and B and then become a parenthesis AB, and you remake another distance matrix based on that, AB as a new taxa or new sequence, and then compare to C and D. And the DCD will be the same as here. So you only need to recalculate these two. And so how do you recalculate that? The new distance between the parentheses AB and C will be DAC plus DBC divided by 2, and the same for the others. So very simple way to recalculate the distance, and you just reform the process again and again until you resolve all the relationship between the sequences. And here is an example. And here are the sequences differences between the different group of animals. You can see some dog, bear, raccoon, weasel, seal, sea lion, cat, and monkey. And so you just need to look at the lower left corner. They are the same for upper right corner of this distance matrix. For all the numbers on the matrix, you just try to look at the lowest number, which means the most similar sequences. In this case, it will be sea lion and seal. Yes, 24. So let's combine seal and C line into another new taxa called SS. And for the other number, they will be the same. And you only need to recalculate these sequences. So you have a new distance matrix. And again, find the smallest number on this table, which would be, I think, right here, bear and raccoon. Is that right? I think so. So bear and raccoon. So we can combine those two together and make another new matrix, and keep going that until everything is resolved like this one. And it'll give you the estimations between of the differences between each group of the taxa, and then reconstruct the phylogenies. And so very simple, right? I hope you understand what I was talking about. It's very simple in this way. But there's some problem could associate to it. I will give you an example right here. And these are, if we know the evolution of the sequences, so this is basically what I make artificially. I try to, I give the computer an original sequences and force the evolution for at a different point. And right here, from here to SP1, it will be 3 substitutions. And to number 2 node, it will have 2 substitutions right here. And I enforce 10 substitution for SP2 and 3 substitution for SP3 from the node 2. Okay, so the branch is corresponding to the differences. Okay, so we can make a distance matrix according to the true tree. So SP1 and SP3 will be 8 differences, 3 plus 2 plus 3, right? And SP1 and SP2 will be 10 plus 2 plus 3 is 15. And the same for SP2 and 3. So you will have 13 for that particular tree, right? So we make this distance matrix. So from this distance matrix, we can use the UPGMA to reconstruct the phylogeny. And SP1 and 3 will be together, and then SP2. So what's going on with this tree and that tree? Are they the same? I don't think they are the same. They are different. SP1 and 3 are the most closely related, but here is SP2 and 3. So what's going on? I calculate from here to here, but they give you another answer. Well, for some of them, I know you probably know because I already talked about a similar case. But for the others, what do you think? What's going on here? I use the logic of the calculation, but it gives you a different answer. Anyone got the answer? Can get an extra point? Just kidding. Let me show you what's going on here. Is there's the distance matrix, and using distance matrix to reconstruct a relationship is based on a similarity. So anything which are more similar will be grouped first. So in the evolution right here, because SP2 has a long branch right there, and which makes SP1 and 3 very similar on this tree, because they are all very different from SP2. So they force the SP3 and SP1 together first, because they are more similar to each other compared to the long branches. It could be more, a lot more branches on the tree. I'll just give you a very simple example here. So that's the major problem in that they ignore some of the possibility for grouping the wrong ones. And in this case, because UPGMA, they assume the rate of evolution along the branch are the same. So on this tree here, from this point to SP2 is 7 from this point to SP1 is 7 as well. So that's the actually that's the meaning for UPGMA. The unweighted pair group method using are arithmetic averages, which give you the same number for the rate of the evolution on the branch. And as we know, in the real world, it's impossible to have the constant rate for the evolution for the branches. So we all know that UPGMA will almost give you the round trees always. So and that's the reason why nobody's using UPGMA if you are dealing with molecular evolution studies. And you still can see that in some ecological studies, and which is just simply clustering the groups. But that's a different things. And but we know there's some methodological problems associated to it. And so be aware. Although we know this is a very simple one, UPGMA, very simple to calculate, easy to get a result, but almost always wrong. So how to avoid that? And there are several other things, and one of the methods try to avoid that is the neighbor joining method, and they does not assume a clock like evolution on the sequences. So it approximates the minimal evolution methods in a way, and I will explain a little bit here. And neighbor joining, as the it infers directly, is to combine the sequences together, but at the same time to calculate the distance, overall distance as a whole, but not only consider the two distance in this case. So the process starts with a star-like tree like this one, and without any resolution right here. So first you will calculate a distance based on this one, and using a theoretical or hypothetical node right here, this x, and to calculate the distance between here and here and here and here and everything, and to sum up all the distance together and as a first measure. And then you will try to combine any two pairs. In this case, it will be any two out of the 8 sequences. And so you will calculate 1 to 2 together, and 1 to 3, and 7 to 8, and calculate everything on this new data set. And to calculate using the new data sets, computing a to y, 2 to y plus x to y to x, and x to 2, and x to 1, and so on. So basically, you'll compare about all the possibilities on the tree and choose one of the most the best tree to go for the next step. And the next step will be try to pull out another pair, including this one as a new branch, and to figure out what is the best tree. So the process keep going on until it resolves everything. And although it does not assume a clock-like structure, but it still suffers from the long branch extraction in a way. We'll mention about that probably next week for a theoretical concern. And for each tip, the actual calculation is something like that. You don't need to remember anything of it. Don't worry about it. And basically, you just need to sum up all the distance I just mentioned of the di divided by n minus 2. And to choose the I and j for each one of the pair, which is the smallest for the distance for all the different combinations. And just calculate and keep going on until you resolve the tree. So this is the process in the calculation, but don't worry about it. Nowadays you just click the computer, you give it a result. So one of the example for calculating the distance and how to incorporate the information of the substitution model is something like this one. So, well, actually I already mentioned this. Probably this should go a little bit earlier. Anyway, so this is the similarity measures for the different sequences, and you just need to recalculate a new distance matrix according to the substitution model. So for the UPGMA model I just mentioned there on previously slides, I just use a very simple estimation without any corrections on the substitution model value. And basically you just transform the distance table into the new table using the new substitution model you choose. And in this case, there's a Juice Cantor model. And for example, the 1 and 2, the value is 0.266. And you just replace the p-value with this number, and you give you the new estimate for substitution per site number, and give you a number right here, and that's the new table for that. And so this is a basic procedure. Here are some of the list for the assumptions on the distance methods, and the first one is it assumes all nucleotide sites change independently, and that's true. There's the same assumption for all the different methods, and which is violated very easily, and because the nucleotide site sometimes does not change independently. They will change according to the loop structure. If you're dealing with the RNA, there's a sequence structure. So if it's the sequences, the substitution is on one side of the loop of the stem, on the stem, then you would likely to change the probability of the corresponding site of the change. So the assumption is very easy to violate, but nobody cares. Anyway. The second one is the substitution rate is constant over time and in different lineages, which is also very easy to violate, but very difficult to evaluate because you cannot go back in time. So again, this is very, very hard to evaluate on this point. The best composition is at equilibrium, and so therefore you can incorporate models, substitution model, into the data sets. But what if it's not? Then you have some problem. But usually we don't really worry about that because we cannot do anything about it anyway. So the probability for the nucleotide substitution are the same for all sites and do not change over time. And if they change from site to site, then we need to have some corrections, and like using different models for the probability of the change among sites, and that's called the gamma distribution, and we'll talk about that later, how to incorporate that into the calculations. So in any way, many of the assumptions can be violated very easily, and which is true for all methods as well.